I want to start with something that Einstein believed with absolute conviction for the last 30 years of his life, something he argued for in papers and in letters and in conversations with colleagues, something he staked his scientific reputation on, and something that experiment has now definitively shown to be wrong. Einstein believed that the universe has a reality that is independent of observation. He believed that when a physicist measures a particle and finds it in a specific state, the particle was already in that state before the measurement, whether or not anyone was looking. He believed that quantum mechanics, with its clouds of probability and its suggestion that particles do not have definite properties until they are measured, was incomplete. That underneath the probabilistic quantum description, there was a deeper, more complete description in which everything had definite values all the time, whether or not anyone looked. He called this belief, informally, the principle that the moon is there when nobody is looking. You do not need to observe the moon for it to exist with definite properties at a definite location. Its existence is not contingent on observation. It is real independently. And he believed that the same was true of every particle, every field, every physical property in the universe. Reality is real. Observation does not create it, it reveals it. Einstein believed that the universe has a reality that is independent of observation. He believed that when a physicist measures a particle and finds it in a specific state, the particle was already in that state before the measurement, whether or not anyone was looking. He believed that quantum mechanics, with its clouds of probability and its suggestion that particles do not have definite properties until they are measured, was incomplete. That underneath the probabilistic quantum description, there was a deeper, more complete description in which everything had definite values all the time, whether or not anyone looked. He called this belief, informally, the principle that the moon is there when nobody is looking. You do not need to observe the moon for it to exist with definite properties at a definite location. Its existence is not contingent on observation. It is real independently. And he believed that the same was true of every particle, every field, every physical property in the universe. Reality is real. Observation does not create it, it reveals it. I want to spend a moment on why Einstein held this belief so strongly, because I think his reasons were not just philosophical stubbornness. He had deep physical intuitions that led him to this position, and those intuitions were not unreasonable. Einstein's primary concern was what he called the completeness of quantum mechanics. In quantum mechanics, two particles can be entangled in such a way that measuring one of them immediately affects the description of the other, no matter how far apart they are. If Alice measures particle A and finds it spin up, then Bob's particle B is immediately described as spin down, even if Bob is on the other side of the galaxy. For Einstein, this seemed to imply one of two things. Either the measurement of A instantaneously affected the physical state of B, which would require a physical influence to travel faster than light, violating special relativity, or the description of B was always spin down before Alice's measurement, and quantum mechanics had simply failed to say so. Einstein strongly preferred the second option. The description of B was always spin down. Quantum mechanics, by failing to assign a definite spin state to B before Alice's measurement, was incomplete. There must be hidden variables that determine the spin states of both particles from the moment of their creation. This reasoning seems natural. And notice that it is not just a philosophical preference for a certain kind of world. It is a physical argument based on the requirements of special relativity. If quantum mechanics is complete, if the state of B really is undefined until Alice measures A, then Alice's measurement must somehow instantaneously affect B regardless of distance. This seems incompatible with the special relativistic prohibition on faster-than-light influences. The resolution of this tension, which took decades to fully work out, is subtle. Quantum mechanics does not violate special relativity, even though the entanglement correlations are instantaneous, because the correlations cannot be used to send information faster than light. Alice's measurement of A gives her a random result. Bob's measurement of B also gives him a random result. It is only when they compare their results at the speed of light at most that they discover the correlation. The correlation is instantaneous at the level of the quantum state. The information about the correlation travels at the speed of light or less. Special relativity is not violated, but in a way that requires careful attention to the distinction between quantum states and information. This is precisely the kind of subtlety that makes quantum mechanics so philosophically challenging. The theory is internally consistent. It does not violate special relativity, but it describes a world in which distant particles are connected in ways that feel, intuitively, like they should require faster-than-light influences. The fact that the connections are real but do not transmit information is one of the most counterintuitive features of the theory. Einstein's concern, expressed in the EPR paper, was a serious physical concern about the consistency of quantum mechanics with special relativity. It was not resolved by showing that quantum mechanics is consistent. It was sharpened by Bell into a precise experimental test. This belief is called local realism. Einstein was wrong about both. Not wrong in the sense of making an error in his reasoning. Wrong in the sense that nature, examined with sufficient precision, does not behave the way his beliefs required. The experiments that demonstrated this, the Bell tests that I've mentioned in earlier videos, reached their definitive culmination in the work that won the Nobel Prize in Physics in 2022, awarded jointly to Elaine Aspect, John Clauser, and Anton Zeilinger for experiments demonstrating the violation of Bell inequalities. And in the years since, the quantum computing revolution has provided a new arena in which these violations can be tested with unprecedented scale, precision, and control, confirming the results with a thoroughness that leaves essentially no room for the alternatives that Einstein would have preferred. The reality that these experiments reveal is not what anyone expected, not what Einstein expected, not what Bohr expected, not what any of the founders of quantum mechanics fully grasped when they developed the theory in the 1920s. The reality they reveal is that the universe, at its fundamental level, does not consist of things that have definite properties when no one is looking. The properties of quantum systems are not hidden variables waiting to be revealed by measurement. They are genuinely indeterminate until the moment of measurement, and the act of measurement is not a passive revelation of pre-existing fact, but an active participation in the creation of physical reality. This is the claim I want to examine today. Not just whether it is supported by experiment, which it is, but what it actually means, what it implies about the nature of reality, what it says about the universe we are living in, and why, when you follow the implications carefully and honestly, they are more disturbing than the headline suggests. Let me begin with the experiment that established all of this, and let me build it up from first principles, because I think it is one of the most beautiful and most philosophically significant experiments in the history of science, and it deserves more than the usual 30-second summary. The experiment is called a Bell test, and to understand it, you need to understand what Bell's theorem says. And to understand Bell's theorem, you need to understand what problem it was addressing. In 1935, Einstein, Boris Podolsky, and Nathan Rosen published a paper that is now known by their initials as the EPR paper. The paper presented what they considered a proof that quantum mechanics was incomplete. The argument was subtle and relied on two premises that Einstein considered self-evident. The first premise was locality. Physical influences cannot propagate faster than light. If two systems are far enough apart and nothing has had time to travel from one to the other, then what happens to one cannot immediately affect the other. The second premise was realism. If you can predict with certainty the outcome of a measurement on a system without disturbing it, then the system has a definite value for that property whether or not you measure it. Using these two premises, Einstein, Podolsky, and Rosen constructed an argument that two entangled particles must each have definite values for certain properties, even though quantum mechanics assigns them only probability amplitudes. Since quantum mechanics does not assign definite values, but the EPR argument shows they must exist, quantum mechanics must be incomplete. There must be additional variables, hidden variables, that quantum mechanics does not describe, but that determine the outcomes of measurements. This was a serious argument, and it was taken seriously. For 2 decades, physicists either accepted it as showing that quantum mechanics was incomplete or dismissed it as philosophically confused without being able to say exactly where the confusion was. This was a serious argument, and it was taken seriously. For 2 decades, physicists either accepted it as showing that quantum mechanics was incomplete or dismissed it as philosophically confused without being able to say exactly where the confusion was. Let me tell you about the intellectual atmosphere in physics during those 2 decades, because I think it explains why Bell's theorem had such a dramatic impact. By the 1950s, quantum mechanics was the most successful physical theory that had ever been developed. Its predictions had been confirmed to extraordinary precision. It had explained the structure of atoms, the behavior of electrons in solids, the properties of superconductors, the nature of chemical bonds. Every attempt to find a situation in which quantum mechanics failed had failed. The theory worked, but the theoretical community was deeply divided about what quantum mechanics meant. Bohr's Copenhagen interpretation, which said that quantum mechanics was complete, that it described probabilities rather than underlying realities, and that the question of what a particle was doing when not being measured was not a meaningful physical question, was the dominant view. But it was not universally accepted. Bohm had developed his hidden variable theory in 1952, showing that it was possible to construct a theory that was empirically equivalent to quantum mechanics, but that assigned definite properties to particles at all times. And Einstein, until his death in 1955, continued to believe that quantum mechanics was incomplete. The debate between these views was genuine and important, but it seemed to many physicists to be unresolvable. Hidden variable theories could be constructed that reproduced all the predictions of quantum mechanics. How could you tell them apart? The question seemed like one of philosophical preference rather than empirical content. Bell's insight in 1964 was to realize that this was wrong. The hidden variable theories that had been constructed were not generic hidden variable theories. They were specific theories with specific assumptions, including the assumption of locality. And locality, Bell showed, made a specific prediction about correlations that was different from the quantum mechanical prediction. You could test whether local hidden variables existed by measuring the correlations and checking whether they exceeded the Bell bound. The mathematical argument is elegant, and I want to sketch it, at least in spirit, because I think it helps to understand why Bell's result is a theorem rather than just a hypothesis. Consider 2 particles that have interacted and separated. Call them particle A and particle B. Each particle has a property, say spin, that can be measured along any direction. When you measure particle A along direction A, you get either up or down. When you measure particle B along direction B, you get either up or down. If the particles are entangled in the way that quantum mechanics describes, the probability of getting specific combinations of results depends on the angle between A and B. In a local hidden variable theory, the result of measuring particle A along direction A is determined by the hidden state of particle A and the direction A. The result of measuring particle B along direction B is determined by the hidden state of particle B and the direction B. The hidden states of the two particles are set at the moment of entanglement and do not change when the measurements are made. In particular, the measurement of particle A does not affect the result for particle B because they are far apart and the measurement is local. Given these assumptions, Bell derived an inequality. If you choose 3 different measurement directions and compute the correlations between measurements on A and B for each pair of directions, the correlations satisfy a specific inequality. The inequality is not derived from any specific hidden variable theory. It is derived from the general assumption of local realism. Any local hidden variable theory, whatever the specific nature of the hidden variables, must satisfy this inequality. Quantum mechanics predicts that the inequality is violated for specific choices of measurement directions. The predicted correlations exceed the bound that any local hidden variable theory can produce. Bell's theorem says either quantum mechanics is wrong or local realism is wrong. You cannot have both. Now Bell's theorem is established, and the Bell tests have definitively confirmed that the Bell inequality is violated. Local realism is wrong. The universe does not consist of locally determined properties. The measurement of particle A does affect the statistics of particle B, even when they are far apart, and there is no time for any signal to travel between them. This is a real physical effect. It is not a loophole in the formalism. It is not a measurement artifact. It has been tested with increasing precision and with increasing rigor for 60 years, and every test confirms the same result. The correlations between entangled particles exceed what any local realistic explanation can account for. I want to say something about the specific loopholes that have been debated, because understanding why the loopholes were important and why they are now closed helps to understand why the result is as definitive as I am claiming. The 3 main loopholes were the detection loophole, the locality loophole, and the freedom of choice loophole. The detection loophole arose because early experiments detected only a fraction of the photons they emitted. If only a subset of particles is detected, and if the detection probability depends on the hidden state in a specific way, then a local hidden variable theory might be able to reproduce the observed correlations even if the true correlations would violate the Bell inequality. Aspects experiments in the 1980s significantly reduced this concern, but did not fully close it. More recent experiments, particularly those using atomic ions rather than photons, have achieved detection efficiencies close to 100%, effectively closing this loophole. The locality loophole arose because in early experiments, the choice of which direction to measure was made before the particles had separated enough to be space-like separated. If the measurement choices were made while the particles could still have communicated, a local hidden variable theory might exploit this to fake the quantum correlations. Aspects 1982 experiment specifically addressed this by using fast random number generators to choose the measurement directions, making the choices after the particles had separated. But the random number generators used were not truly random. They were pseudo-random, which left open the possibility that the hidden variables could have predicted the choices. Subsequent experiments, including the famous Big Bell test of 2016, in which hundreds of thousands of volunteers contributed random choices generated by playing a video game, have addressed this concern with increasing rigor. The freedom of choice loophole is perhaps the most philosophically interesting. It notes that for the Bell test to be truly conclusive, the measurement choices must be genuinely free and independent of the hidden state of the particles. If the measurement choices are correlated with the hidden state, even if that correlation was established in the distant past, then a local hidden variable theory might be able to explain the correlations. The most extreme version of this concern is the cosmic conspiracy idea, in which the hidden state of the particles is correlated with the hidden state of the random number generators or the cosmic photons or the neurons of the experimenters, all the way back to the Big Bang. This concern cannot be definitively addressed by any finite experiment, but it can be pushed back further and further. The Big Bell test addressed it by having the measurement choices generated by human decisions rather than physical random number generators. The Cosmic Bell test of 2017, led by Zeilinger, addressed it by having the measurement choices determined by the colors of photons received from distant quasars, one set of quasars about 600 light years away and another about 1,800 light years away. For the local hidden variable explanation to work in this experiment, the correlation between the hidden states of the particles and the hidden states of the quasars would have had to be established at least 600 to 1,800 years ago before the quasar photons were emitted. While not impossible, this requires an increasingly implausible conspiracy between the experimental setup and the physical universe. The 2022 Nobel Prize was awarded specifically for experiments that closed the main loopholes, simultaneously providing the most rigorous confirmation that local realism is incompatible with the observed quantum correlations. Then, in 1964, John Bell found the confusion, or rather, he found something more devastating than a confusion. If local realism is correct, if particles have definite hidden properties that are set at the moment of entanglement, then the correlations between measurements on the two particles are bounded by a specific mathematical inequality. This is Bell's inequality. The key insight is that quantum mechanics predicts correlations that violate Bell's inequality, not by a small amount, by a mathematically clean and unambiguous amount. Bell's theorem is a proof, not an experimental result. It is a mathematical theorem that says, if local realism is correct, then quantum mechanics is wrong. If quantum mechanics is correct, then local realism is wrong. The two are mathematically incompatible. This was not just another interpretation of quantum mechanics. It was a mathematical proof that the question of whether particles have definite properties before measurement was not a philosophical matter of taste. It was a question that could be tested experimentally. And in the 1970s and 1980s, it was tested. The first decisive experiments were done by John Clauser and his collaborators using photon pairs and measuring their polarization correlations. Later, Alain Aspect performed more rigorous experiments that closed several loopholes that skeptics had identified. And in subsequent decades, increasingly sophisticated experiments by Zeilinger and many others tightened the constraints further. The results were unambiguous. Bell's inequality was violated by the amount that quantum mechanics predicted over and over, with different particles, different laboratories, different experimental setups. Local realism is wrong. The universe does not work the way Einstein believed. Now I want to take you deeper into what the violation of Bell's inequality actually means, because the popular summary that quantum mechanics has defeated local realism is correct, but does not convey the full depth of the implications. There are several different responses to Bell's theorem, and they lead to very different pictures of what reality is like. The first response is to accept both the failure of locality and the failure of realism. This is the Everett interpretation, the many worlds picture, that I discussed in the universal wave function video. In the many worlds interpretation, measurement does not collapse a wave function. The universe branches. Both outcomes happen. The correlations between entangled particles are not mysterious non-local influences. They are correlations encoded in the branching structure of the universal wave function, correlations that are perfectly local in the four-dimensional space-time block. The apparent non-locality is an artifact of looking at only one branch. The many worlds interpretation is not obviously wrong. It is mathematically consistent. It takes the Schrödinger equation completely seriously. but it commits to an ontology so extravagant, an infinite multiplicity of equally real branches, that many physicists and philosophers find it difficult to accept. The second response is to accept the failure of realism while preserving locality in a modified sense. This is the Copenhagen interpretation, the view that quantum mechanics is a complete description of reality, that particles do not have definite properties before measurement, that the wave function is the most complete description of a quantum system, and that the question of what a particle is doing when no one is looking is not a meaningful physical question. On this view, the correlations in Bell tests are explained by the quantum mechanical formalism without invoking any non-local influence. The correlations are real, but they do not involve anything traveling faster than light. They are correlations in a quantum state, and quantum states are not the kinds of things that have locations or that transmit influences. The Copenhagen interpretation has been the dominant framework in physics since the 1920s. It is what is taught in most physics courses. It is what most working physicists use when they calculate predictions and compare them to experiments. But it has a deep, unsatisfying quality, which is that it refuses to answer the question of what the wave function means. Is the wave function a description of reality, or is it a description of our knowledge of reality? If it describes reality, what kind of reality is it? If it describes knowledge, whose knowledge, and what is the underlying reality that the knowledge is knowledge about? Copenhagen famously tells physicists not to ask these questions and to focus on calculating predictions. Shut up and calculate, as the physicist David Merman summarized it with characteristic acerbity. This is useful advice for physicists doing physics. It is not satisfying for anyone who wants to understand what the physics is actually telling us about the nature of reality. The third response is to accept the failure of locality while preserving realism. This is the Bohmian mechanics interpretation, or pilot wave theory, developed by David Bohm in 1952. In Bohm's theory, particles do have definite positions at all times, whether or not they are being observed. The moon is there when nobody is looking. The apparent indeterminacy of quantum mechanics arises not from the absence of definite properties, but from our ignorance of those properties. The wave function is real, but it acts as a pilot wave that guides the motion of particles, and the initial positions of particles are unknown to us. Measurement outcomes look random because they depend on the exact initial positions, which are hidden from us. Bohmian mechanics makes the same predictions as standard quantum mechanics for all experiments. It is empirically equivalent, but it restores realism at the cost of non-locality. In Bohmian mechanics, the pilot wave influences particles instantaneously across any distance. When you measure one particle of an entangled pair and affect its pilot wave, the other particle's motion is instantaneously influenced, no matter how far away it is. The Bell correlations are explained by this non-local influence. This non-locality is troubling. It seems to conflict with special relativity, which says that influences cannot propagate faster than light. Bohmians argue that the non-locality is not signalable, that you cannot use it to send information faster than light, because the results of individual measurements are still random. Only the correlations between distant measurements are non-local, and you need to compare notes between the two measurement sites at the speed of light to see the correlations. So special relativity is not technically violated, but the non-locality is there at the level of the physical reality, even if not at the level of information transfer. The Copenhagen interpretation has been the dominant framework in physics since the 1920s. It is what is taught in most physics courses. It is what most working physicists use when they calculate predictions and compare them to experiments. But it has a deep, unsatisfying quality, which is that it refuses to answer the question of what the wave function means. Is the wave function a description of reality, or is it a description of our knowledge of reality? If it describes reality, what kind of reality is it? if it describes knowledge, whose knowledge and what is the underlying reality that the knowledge is knowledge about, Copenhagen famously tells physicists not to ask these questions and to focus on calculating predictions. Shut up and calculate, as the physicist David Merman summarized it with characteristic acerbity. This is useful advice for physicists doing physics. It is not satisfying for anyone who wants to understand what the physics is actually telling us about the nature of reality. I want to be a little more specific about why Copenhagen is unsatisfying, because I think the dissatisfaction is often described vaguely, and it deserves to be stated precisely. The Copenhagen interpretation draws a sharp distinction between the quantum system and the classical measurement apparatus. The quantum system is described by the wave function. The measurement apparatus is described classically. The wave function gives probabilities for measurement outcomes when the quantum system interacts with the apparatus. The problem is that the distinction between quantum system and classical apparatus is not given by the physics, it is chosen by the physicist. The Heisenberg cut, the boundary between the quantum and classical descriptions, can be placed anywhere. You can include more or less of the measurement apparatus in the quantum description. Different placements of the cut give the same predictions for measurement outcomes, but they give different accounts of where the wave function collapse happens. This is deeply unsatisfying because it means that the physical description of the world depends on a choice made by the observer, not on any physical fact about the world. The universe does not have a preferred quantum classical boundary. The physicist imposes one, and different physicists imposing different boundaries describe the same physical situation differently. This is not what we expect from a fundamental physical theory. We expect the description to be about the world, not about the perspective of the describer. The many worlds interpretation avoids this problem by removing the quantum classical boundary entirely. Everything is quantum. The wave function of the universe evolves according to the Schrödinger equation without any collapse. When a measurement happens, the universe branches. Both outcomes occur each in its own branch. The apparent collapse of the wave function that we experience is the result of finding ourselves in one branch after the branching has occurred. There is no collapse. There is only branching. This is mathematically elegant and philosophically consistent, but it has its own problems. One is the problem of the preferred basis. When the universe branches, in what basis does it branch? The Schrödinger equation does not single out any particular basis as the one in which branching occurs. But we experience a world in which things have definite positions, definite momenta, definite energies. Why these observables rather than others? The answer from the many worlds interpretation involves decoherence, the process by which quantum systems become entangled with their environments, which selects certain bases as the effectively classical ones. But the decoherence argument has subtleties that are still debated. Another problem is the probability problem. In the many worlds interpretation, all branches exist. But when we do quantum mechanics, we assign different probabilities to different outcomes. What do these probabilities mean in a world where all outcomes happen? Why do we experience probabilities that follow the Born rule, the quantum mechanical rule for computing probabilities from wave functions? This is a deep question that has been addressed by David Deutsch and others using decision theoretic arguments, but it remains controversial. The Bohmian mechanics interpretation avoids both the quantum classical boundary problem and the probability problem at the cost of introducing a real physical wave function that guides the motion of particles non-locally. In Bohm's theory, the wave function is real. It is not just a calculational tool. It is a physical field that permeates all of space and that influences the motion of particles. And the motion of a particle is influenced instantaneously by the wave function everywhere, including in regions far from the particle. This non-locality is real. In Bohm's theory, It is not a statistical correlation. It is a physical influence that propagates instantaneously. The particle at location A is genuinely influenced in real time by what is happening to the entangled particle at location B, regardless of how far apart they are. The Bell correlations are explained by this non-local influence. Bohmian mechanics is a hidden variable theory, but it is not a local hidden variable theory. The hidden variables are the particle positions, which are definite at all times and which the wave function guides. The non-locality is the price paid for maintaining the hidden variables. Bell's theorem rules out local hidden variables but not non-local ones. And Bohm's theory is a specific and well-developed non-local hidden variable theory. What makes Bohmian mechanics interesting, beyond its consistency, is that it shows that the strangeness of quantum mechanics is not in the fact that particles do not have definite positions. In Bohm's theory, they do. The strangeness is in the non-local guidance. The world is not strange because things do not have properties. It is strange because the properties of distant things are connected instantaneously in ways that cannot be accounted for by any local mechanism. All three interpretations, Copenhagen, many worlds, and Bohmian mechanics, are empirically equivalent. They make the same predictions for all experiments. There is no experiment that distinguishes between them. The choice between them is a choice about what kind of story you want to tell about the underlying reality, not a choice forced by the data. This is perhaps the most unsettling aspect of the quantum mechanics situation. The theory works perfectly. Its predictions are confirmed at every scale and every precision, but the theory underdetermines its own ontology. The same empirically successful formalism is consistent with a world in which particles do not have definite properties until measured, a world in which everything is quantum and the universe branches at every measurement, and a world in which particles have definite properties at all times, but the wave function that guides them is non-local. These are very different worlds, and the data cannot tell us which one we are in. Now let me tell you about where quantum computers come into this story. Quantum computers are devices that exploit quantum superposition and quantum entanglement to perform computations that are, for specific problems, dramatically more efficient than classical computers. They do this by maintaining quantum systems and superpositions of many states simultaneously and allowing those states to interfere with each other in ways that amplify the probability of the correct answer and suppress the probability wrong answers. The key resource that quantum computers exploit is entanglement. In a quantum computer with 50 qubits, those 50 qubits can be entangled in ways that create a superposition of 2 to the 50 states simultaneously, roughly 1,000 trillion states at once. The quantum computation manipulates all of those states in parallel, performing what amounts to a massively parallel computation in a single physical system. But here is the connection to Bell's theorem. Quantum computers require that the correlations between their qubits be genuinely quantum mechanical, genuinely entangled, genuinely non-classical. If the correlations could be described by hidden variables, if the apparent entanglement were just classical correlation between hidden properties, then quantum computers would not work. The speedup they provide for certain problems depends specifically on the quantum nature of the correlations. This means that the operation of a quantum computer is itself a test of quantum mechanics over hidden variable theories. Every time a quantum computer correctly solves a problem that requires genuine quantum entanglement, it is demonstrating that the correlations it uses are not classical, they are quantum. And quantum correlations violate Bell's inequalities. Researchers have now used quantum computers with dozens to hundreds of qubits to perform Bell tests at a scale that was previously impossible. Instead of testing correlations between pairs of particles, they can test correlations in systems of many entangled qubits simultaneously, verifying that the quantum mechanical predictions hold across the entire system. These tests, while they have different technical characteristics from the original two-particle Bell tests, provide a new and complementary form of evidence for the quantum nature of correlations. And the results are consistent with quantum mechanics and incompatible with local hidden variable theories as expected. But the quantum computing context adds something important that the original Bell tests lacked. In the original Bell tests, there was always the question of whether the specific experimental setup, the specific choice of particles and measurements, somehow biased the results. The loopholes that Aspect and Zeilinger worked to close, the detection loophole, the locality loophole, the freedom of choice loophole, were all concerns about whether the experimental setup was somehow compatible with a hidden variable explanation. In quantum computing, the question is different. The question is not whether this specific experiment could be explained by hidden variables. The question is whether a device that provides genuine computational speedup can be explained by hidden variables. And the answer is no, by a mathematical proof, not just by an experimental test. This is why I said that quantum computers have proved, in a sense different from but complementary to the Bell tests, that reality does not consist of hidden variables. Any computational advantage of a quantum computer over a classical one depends on quantum correlations that cannot be reproduced by local hidden variables. The proof is not experimental, it is mathematical. It follows from the theory of quantum computing and from Bell's theorem. Researchers have now used quantum computers with dozens to hundreds of qubits to perform Bell tests at a scale that was previously impossible. Instead of testing correlations between pairs of particles, they can test correlations in systems of many entangled qubits, simultaneously verifying that the quantum mechanical predictions hold across the entire system. These tests, while they have different technical characteristics from the original two-particle Bell tests, provide a new and complementary form of evidence for the quantum nature of correlations. And the results are consistent with quantum mechanics and incompatible with local hidden variable theories as expected. But the quantum computing context adds something important that the original Bell tests lacked. In the original Bell tests, there was always the question of whether the specific experimental setup, the specific choice of particles and measurements, somehow biased the results. The loopholes that Aspect and Zeilinger worked to close, the detection loophole, the locality loophole, the freedom of choice loophole, were all concerns about whether the experimental setup was somehow compatible with a hidden variable explanation. In quantum computing, the question is different. The question is not whether this specific experiment could be explained by hidden variables. The question is whether a device that provides genuine computational speedup can be explained by hidden variables. And the answer is no, by a mathematical proof, not just by an experimental test. Beyond quantum computers, there is another application of quantum non-locality that I find both practically important and philosophically remarkable. Quantum teleportation. Quantum teleportation is not the science fiction version of teleportation in which a physical object is disassembled in one place and reassembled in another. It is something more subtle and in some ways more interesting. It is a process by which the complete quantum state of a particle can be transferred from one location to another using entanglement and classical communication. The process works as follows. Alice and Bob share an entangled pair of particles. Alice has a third particle whose quantum state she wants to send to Bob. She performs a specific measurement on her particle and on one of the entangled pair. The measurement outcome, which is random and gives Alice no useful information about the state of the third particle, is 2 classical bits. Alice sends those 2 classical bits to Bob. Bob, upon receiving them, performs a specific operation on his half of the entangled pair, determined by the 2 classical bits. After the operation, Bob's particle is in exactly the state that Alice's original particle was in. The state has been teleported. What is remarkable about this process is that the quantum state has been transmitted without the quantum state itself traveling through space. The classical bits that travel from Alice to Bob carry no information about the state. The quantum information is somehow distributed between the entangled pair and the classical bits in a way that only comes together at Bob's location after the classical bits arrive. The non-locality of the entanglement is doing something that classical communication alone cannot do. Quantum teleportation has been experimentally demonstrated many times with particles of various kinds over distances ranging from laboratory scale to several hundred kilometers using optical fibers and satellite links. It is a real phenomenon, and it depends on the genuine non-locality of quantum entanglement. If entanglement were just classical correlation between hidden properties, quantum teleportation would not work. This is why I said that quantum computers proved something, not just confirmed something. The computational power of quantum computers, demonstrated by specific algorithms that solve problems exponentially faster than classical computers, and the operational success of quantum teleportation, demonstrated by direct experimental implementation, are both consequences of genuine quantum non-locality. They are proofs in the sense of demonstrations that the non-locality is real and that it cannot be reduced to classical hidden variables. This is why I said that quantum computers proved something in the title of this video, not just confirmed something. The computational power of quantum computers, demonstrated by specific algorithms that solve problems exponentially faster than classical computers, is a consequence of genuine quantum non-locality. It is a proof that the non-locality is real and that it cannot be reduced to classical hidden variables. Now I want to take you to the implications, because this is where the conversation usually stops and where I think it should continue. Most discussions of quantum non-locality and the failure of local realism treat the result as a curiosity, a strange feature of the quantum world that has no practical implications for the large-scale world we inhabit. After all, quantum effects are small. They operate at the level of individual particles. The macroscopic world, the world of tables and planets and people, behaves classically. The correlations that violate Bell's inequalities are statistical, distributed over many measurements. In any single measurement, the result is definite. How can the weird quantum correlations of microscopic particles have any implications for the nature of reality at the scale we experience? This dismissal is understandable, but I think it is wrong. Let me explain why. The first implication is about the completeness of any physical description. If physical properties do not exist prior to measurement, if the world does not consist of things with definite values that measurement merely reveals, then any complete description of the world must look different from what we intuitively expect. It cannot be a list of objects with properties. It must be something more like a description of potentialities, of what would happen under various conditions, rather than a description of what is the case independently of conditions. This has implications for the concept of physical explanation. When we explain a phenomenon, we usually do it by saying what the things are that produce it and what properties they have. The bridge collapsed because the steel was weak. The star formed because the gas cloud was dense enough. The drug worked because it bound to the receptor. In each case, the explanation refers to things with properties, and the properties are supposed to be real independently of our observing them. But if the failure of local realism means that things do not have definite properties until they are measured, then this whole picture of explanation is called into question. Not because quantum effects are directly relevant to the collapse of a bridge, but because the conceptual foundation on which the ordinary explanation rests, the assumption that things have properties, is not as secure as we assumed. The violation of Bell's inequalities is a demonstration that at the deepest level, the universe does not work that way. The second implication concerns the relationship between the observer and the observed. In classical physics, the observer is irrelevant to the description of the physical world. The world is what it is, regardless of who is looking at it or measuring it. The observer can be idealized away. The wave functions of quantum mechanics, and more fundamentally the Bell experiments, suggest that this idealization is not valid. The act of measurement is not a passive revelation. It is an interaction that affects the system being measured. And in the case of entangled systems, a measurement on one part of the system affects the quantum state of another part instantaneously, regardless of distance. This does not mean that consciousness creates reality. I want to be careful to avoid that misinterpretation, which is common in popular accounts of quantum mechanics. The experiments do not show that a human mind looking at a particle causes it to have definite properties. They show that any physical interaction that constitutes a measurement, whether carried out by a human physicist or an automated detector or any sufficiently large classical system, causes the quantum system to appear to have definite properties. The relevant distinction is not between conscious and unconscious observers. It is between quantum systems, which can be in superpositions, and classical systems, which cannot, at least not in any practical sense. But this distinction itself raises a deep question. What makes a system classical? What determines whether an interaction counts as a measurement? This is the measurement problem that I discussed in the universal wave function video, and it has not been solved. The boundary between quantum and classical is not given by the physics. It is not at a specific scale or a specific mass or a specific temperature. The boundary is wherever we choose to put it, and different interpretations of quantum mechanics put it in different places. The Copenhagen interpretation says the boundary is wherever we put our measurement devices, and it refuses to say more. The many worlds interpretation says there is no boundary. Everything is quantum. And what looks like a boundary is just the branching of the wave function. Bohmian mechanics says particles are always classical in the sense of having definite positions, but the wave function that guides them is non-local. Each interpretation draws the boundary differently, and none of them is fully satisfying. The third implication is about information. One of the most important results in the foundations of quantum mechanics in the last few decades is the theorem that quantum information cannot be copied. This is called the no-cloning theorem, and it says that it is impossible to create a perfect copy of an arbitrary quantum state. The theorem follows directly from the linearity of quantum mechanics, and it has profound implications. For one thing, it means that quantum information is fundamentally different from classical information. Classical information can be copied arbitrarily. You can duplicate a file on a computer. You can photocopy a document. The information is encoded in properties of matter that can be reproduced. Quantum information cannot be copied because the properties that encode it, the quantum states of particles, cannot be reproduced without disturbing the original. For another thing, the no-cloning theorem implies that quantum information, once dispersed, cannot be retrieved by copying the individual parts. When a quantum system interacts with its environment and decoheres, the quantum information about its initial state is not destroyed. It is encoded in the correlations between the system and the environment. But it cannot be retrieved by examining the parts individually. You would need to do a quantum measurement on the entire system plus environment simultaneously, which is practically impossible for any macroscopic system. This connection between quantum non-locality and information theory is one of the deepest results in modern physics, and it is still being actively developed. The quantum error correction codes that make quantum computers reliable are based on exploiting entanglement to distribute information in ways that protect it from errors. The black hole information paradox, which I discussed in the Physics of Death video, is fundamentally a question about what happens to quantum information that falls into a black hole. The connection between the non-locality of quantum mechanics and the structure of space-time and theories of quantum gravity is one of the most active research areas in theoretical physics. For one thing, it means that quantum information is fundamentally different from classical information. Classical information can be copied arbitrarily. You can duplicate a file on a computer. You can photocopy a document. The information is encoded in properties of matter that can be reproduced. Quantum information cannot be copied because the properties that encode it, the quantum states of particles, cannot be reproduced without disturbing the original. The no-cloning theorem has a profound implication that connects back to the Bell experiments. In a local hidden variable theory, information about the hidden state of a particle could, in principle, be copied. If the particle has a definite spin-up in some direction, that is a definite fact about the particle, and there is no reason in principle why you could not measure it and record it and copy the record. But in quantum mechanics, you cannot do this. The quantum state of a particle, its wave function, cannot be copied. And this is not a practical limitation. It is a consequence of the mathematical structure of quantum mechanics, specifically of the linearity of the Schrödinger equation. The fact that quantum information cannot be copied has extraordinary practical consequences, some beneficial and some unsettling. On the beneficial side, it is the basis of quantum cryptography. In quantum key distribution, a key is encoded in quantum states and sent from one party to another. Any attempt by an eavesdropper to copy the quantum key necessarily disturbs the quantum state, alerting the legitimate parties to the presence of the eavesdropper. The security of quantum cryptography is not based on the computational difficulty of breaking a code. It is based on the physical impossibility of copying quantum information without disturbance. On the unsettling side, the no-cloning theorem is connected to the black hole information paradox. When matter falls into a black hole, its quantum information is encoded in the quantum state of the matter. When the black hole evaporates through Hawking radiation, that quantum information must be preserved because quantum mechanics is unitary, and unitarity implies conservation of information. But the information cannot be copied. It cannot exist both inside the black hole and in the Hawking radiation. This is the information paradox. The resolution of this paradox, which I discussed in the Physics of Death video, required the development of new ideas about the relationship between quantum mechanics and space-time, ideas that are still being actively developed. The no-cloning theorem, quantum cryptography, the black hole information paradox, the quantum error correction codes that make quantum computers reliable, all of these are consequences of the same underlying physics. They are consequences of the fact that quantum information is a different kind of information from classical information, and that difference is rooted in the non-locality of quantum mechanics that the Bell experiments have confirmed. For another thing, the no-cloning theorem implies that quantum information, once dispersed, cannot be retrieved by copying the individual parts. When a quantum system interacts with its environment and decoheres, the quantum information about its initial state is not destroyed. It is encoded in the correlations between the system and the environment, but it cannot be retrieved by examining the parts individually. You would need to do a quantum measurement on the entire system plus environment simultaneously, which is practically impossible for any macroscopic system. This connection between quantum non-locality and information theory is one of the deepest results in modern physics, and it is still being actively developed. The quantum error correction codes that make quantum computers reliable are based on exploiting entanglement to distribute information in ways that protect it from errors. The black hole information paradox, which I discussed in the Physics of Death video, is fundamentally a question about what happens to quantum information that falls into a black hole. The connection between the non-locality of quantum mechanics and the structure of space-time and theories of quantum gravity is one of the most active research areas in theoretical physics. All of this, the quantum computing revolution, the quantum error correction codes, the AD-CFT correspondence, the resolution of the black hole information paradox, descends from the Bell experiments and from the failure of local realism. It is a consequence of the fact that reality does not consist of things with definite properties. It is a consequence of the fact that entanglement is real and non-local and cannot be reduced to classical correlations between hidden properties. The fourth implication is the most personal and the most difficult to sit with. If reality does not consist of things with definite properties when no one is looking, what is the nature of the everyday world we experience? The table in front of you, the chair you are sitting on, the room around you, do these things not have definite properties when you are not looking at them? The answer that physics gives is subtle and not the simple one that the headline suggests. The table and the chair and the room are made of an enormous number of quantum particles, each of which does not have definite properties in the quantum sense. But those particles are entangled with each other and with their environment in such a way that for any practical purpose, they behave classically. Decoherence, the process I discussed in the universal wave function video, ensures that the quantum superpositions of macroscopic objects collapse so rapidly that we cannot observe them. The decoherence time for a dust particle, a grain of sand, is something like 10 to the minus 36 seconds, effectively instantaneous. The quantum superpositions of macroscopic objects never have time to develop before they are destroyed by interaction with the environment. This means that the table does have definite properties in the practical sense. It is at a definite location. It has a definite shape and a definite color and a definite temperature. Not because it has hidden quantum properties that are definite at all times in the Bohmian sense, but because the interactions that constitute measurement happen so quickly and so continuously at the macroscopic scale that the quantum indeterminacy never manifests in any observable way. But this resolution of the apparent contradiction, the fact that macroscopic objects behave classically because of decoherence, should not be taken as a complete answer to the question of whether reality exists when nobody is looking. Decoherence explains why we do not observe quantum superpositions in macroscopic objects. It does not explain what is actually there when we are not looking. It does not answer the realist's question: what is the underlying reality that the decoherence process is operating on? The Bohmian says definite particle positions guided by a non-local wave function. The Copenhagenist says the question is meaningless. There is no underlying reality separate from measurements. The Everettian says the universal wave function, branching at every measurement, with all branches equally real. Each answer is consistent with the experimental predictions of quantum mechanics. None is obviously correct. And the choice between them is not a scientific question in the usual sense. It is a question about the interpretation of the formalism, about what the equations are actually describing, about the ontology of quantum mechanics. This is the situation we are in. We have a theory, quantum mechanics, that is the most precisely confirmed theory in the history of science. We have experiments, the Bell tests, that definitively rule out the most natural picture of reality, the picture in which things have definite properties independently of observation. And we have multiple interpretations of what the theory is telling us about what the underlying reality is actually like, none of which is fully satisfying and none of which can be distinguished by any experiment. The implications are worse than the headline suggests, not because quantum mechanics implies that reality is an illusion, which it does not, but because it implies that our deepest intuitions about the nature of reality, intuitions so fundamental that they are built into the language we use to describe the world and the concepts we use to explain it, are not reliable guides to what the world is actually like at the most fundamental level. The world is not made of things with definite properties. The world is made of something, but the something it is made of does not behave the way things with definite properties behave. It is correlated in ways that local properties cannot explain. It responds to measurement in ways that pre-existing properties cannot account for. It is, in whatever sense, the equations of quantum mechanics can be given a physical interpretation more like a web of relationships and potentialities than a collection of objects with fixed attributes. And this is not a feature of the world at some remote quantum scale that has no connection to the everyday world. It is a feature of the same particles that make up your body, the same atoms that make up the table in front of you, the same fields that permeate the space you inhabit. The classicality of the everyday world is a consequence of decoherence, a process that operates on quantum systems that do not have definite properties. The classical world emerges from the quantum world. The quantum world does not emerge from the classical world. The strangeness is the foundation. The normalcy is the emergent approximation. I want to close with something that I think is the most important thing I can say about the implications of the Bell experiments for the way we understand our place in the universe. The violation of local realism tells us that the universe is fundamentally different from what our intuitions suggest. This is not new information, exactly. Physics has been telling us this since Copernicus removed the Earth from the center of the solar system, since Darwin explained the diversity of life without appeal to design, since Einstein curved space-time, since Bohr and Heisenberg and Schrödinger quantized the atom. At every step, the universe has turned out to be stranger than intuition suggests. But the Bell experiments are different from those other revolutions in a specific way. The earlier revolutions changed our picture of the large-scale structure of reality. They moved the Earth, or extended the timescale of life, or curved space-time, but they left intact the basic picture of a world made of things with properties. Atoms have positions and velocities. Planets orbit in definite paths. DNA has a definite sequence. The world is strange at the large scale, but at the small scale, it is made of definite stuff with definite properties. The Bell experiments remove that foundation. They say that even at the small scale, even at the level of individual particles, the picture of definite stuff with definite properties is not correct. The foundation of the intuitive picture of reality is not just challenged at the large scale. It is removed at the small scale. And without that foundation, the large-scale picture that we built on top of it is revealed to be an approximation, an emergent phenomenon, useful and accurate at the scales we inhabit, but not reflective of the deeper structure of what the world actually is. This is why the implications are worse than the headline suggests. The headline says that reality does not exist when nobody is looking. That sounds like a curiosity, a strange feature of the quantum world with no practical significance. But the deeper implication is that the concept of reality that the headline is invoking, the concept of a world made of things with definite properties, is not just violated at some exotic quantum scale. It is violated at the most fundamental level of description. And the world we live in is built on that level. We live in the emergent approximation. We live in the classical behavior that decoherence produces from the quantum substrate. We live in the stable, persistent, definite-looking world that quantum mechanics generates when it is applied to the vast number of particles that make up macroscopic objects. And that world is real in every practical sense. The table is there. The chair is solid. The room has definite dimensions. None of that is challenged by the Bell experiments. What is challenged is the assumption that the definiteness we experience is the fundamental nature of reality rather than an emergent feature of it. What is challenged is the assumption that the universe, at its deepest level, consists of things with properties. What is challenged is the assumption that our intuitions about reality, intuitions built up over millions of years of evolution in a classical world are reliable guides to the nature of reality at the level where quantum mechanics operates. Reality does not exist when nobody is looking in the specific technical sense that quantum systems do not have definite values for all their properties independent of measurement. And the implications of that specific technical claim, followed honestly to their conclusion, take us to a picture of the universe that is genuinely strange in ways that matter for how we think about what we know and how we know it. I want to close by saying something about the future of this line of research, because I think it is important not to leave the impression that the Bell experiments have settled all the questions. They have settled one question definitively. Local realism is wrong. But they have opened up many more questions, and the exploration of those questions is one of the most active and most exciting areas of physics. One of the most important open questions is the relationship between quantum non-locality and the structure of space-time. The non-locality of quantum mechanics, the instantaneous correlations between entangled particles regardless of distance, seems in tension with the local structure of space-time in general relativity. In general relativity, everything propagates locally, each event influencing only its immediate neighbors. The apparent non-locality of quantum mechanics, even though it cannot be used to send information faster than light, seems to require some kind of structure in the universe that allows distant events to be correlated in ways that local physics cannot explain. The most promising attempt to understand this relationship comes from the work on the ADS-CFT correspondence, the duality between quantum gravity in a curved spacetime and a quantum field theory on the boundary of that spacetime. In this framework, the entanglement between parts of the boundary quantum field theory is connected to the geometry of the bulk spacetime. Specifically, the area of a surface in the bulk spacetime is related to the entanglement entropy of the corresponding region of the boundary. This is the Ryu-Takanagi formula, one of the most important results in quantum gravity in the last 20 years. What this suggests is that space-time geometry is, in some sense, built from quantum entanglement. The non-locality of quantum mechanics, rather than being in tension with the local structure of space-time, might be what generates the local structure of space-time. Space-time might be an emergent phenomenon, arising from the pattern of entanglement in a more fundamental quantum system. This is a speculative and actively debated idea. It has not been fully developed into a complete theory, but it connects the Bell experiments through quantum information theory to the deepest questions about the nature of space and time. The non-locality that the Bell experiments have demonstrated might be not just a strange feature of the quantum world, but a clue to the origin of the geometric structure of reality. Another open question is the extent to which quantum non-locality can be harnessed for practical applications beyond quantum computing and quantum cryptography. Quantum sensing, for example, uses entanglement to measure physical quantities with precision beyond what is achievable with classical sensors. Entangled photons can be used to create images with resolution beyond the classical diffraction limit. Entangled atomic clocks can achieve timing precision beyond what is possible with classical clocks. These applications are currently in the research stage, but they illustrate that the non-locality of quantum mechanics is not just a philosophical curiosity. It is a physical resource that can be used to do things that classical physics cannot do. And there is the question of what quantum mechanics becomes at the intersection with gravity. The Bell experiments were done in regimes where gravity is negligible. The quantum systems involved are tiny, and the gravitational forces between them are completely irrelevant. But in the extreme conditions near black holes or in the early universe, quantum mechanics and gravity both matter. What does quantum non-locality look like in curved space-time? How does the entanglement between quantum systems behave near a black hole horizon? These questions are at the frontier of current research, and their answers may change our understanding of both quantum mechanics and general relativity. The experiments that demonstrated the violation of Bell's inequalities and the experiments that run on quantum computers are not the end of the story, they are the beginning. They establish that the universe is quantum, that quantum non-locality is real, that local realism is wrong. Now the project is to understand what the universe actually is at the most fundamental level, given that it is quantum and non-local and strange in the ways the experiments have revealed. Einstein believed the moon is there when nobody is looking, but the particles that make up the moon do not have definite properties in the deeper quantum sense. The moon's definiteness is an emergent phenomenon, a consequence of the quantum substrate organizing itself in ways that produce classical behavior at large scales. This is not a comforting conclusion. It is an honest one. The universe is not made of definite things. It is made of something from which definite things emerge under the right conditions. And the right conditions are the conditions of our everyday experience, the conditions of the macroscopic world, the conditions that evolution built our intuitions to navigate. But those conditions are not the fundamental conditions. The fundamental conditions are quantum mechanical. The fundamental reality is quantum mechanical. And quantum reality, as the Bell experiments have definitively demonstrated, does not consist of things with definite properties when nobody is looking. The implications are not that reality is an illusion. They are that reality is real but strange. Stranger than our intuitions can comfortably accommodate. Stranger than even the founders of quantum mechanics fully grasped when they first encountered the equations. And stranger in a way that is not going to be resolved by better technology or more precise experiments. The strangeness is a feature of the formalism itself, a feature of the equations that have been confirmed to 1 part in a billion by the most precise experiments in the history of science. The strangeness is the physics. And knowing that is, I think, one of the most important things that modern science has to tell us about the universe we inhabit. Not because it changes how we live our daily lives. It does not, in any practical sense. But because it changes the relationship between our experience of the world and what we know the world to be. The world we experience is the classical approximation. What we know from the Bell experiments and from quantum computing and from every precision test of quantum mechanics ever conducted is that the underlying reality is something altogether more subtle, more relational, more dependent on the conditions of observation than any previous picture of reality has ever suggested. Reality does not exist when nobody is looking in the specific technical sense that quantum systems do not have definite values for all their properties independent of measurement. And the implications of that specific technical claim, followed honestly to their conclusion, take us to a picture of the universe that is genuinely strange in ways that matter for how we think about what we know and how we know it. If this changed how you think about the nature of reality, if the Bell experiments look different to you now than they did before, tell me in the comments. Tell me which interpretation of quantum mechanics you find most compelling and why. Tell me whether the strangeness of the quantum world feels like a problem to be solved or a feature to be accepted. And subscribe if you want to keep going into the places where the physics is most precise and the implications are most profound, because that is where the most important questions always are. Suggested titles, 3 options. Quantum computers just prove that reality does not exist when nobody is looking and the implications are worse than you think, Brian Greene. The experiment that proved Einstein wrong about reality and what it actually means, Brian Greene. Bell's theorem destroyed the most fundamental assumption in physics. Here is what replaced it, Brian Greene. YouTube description. Einstein believed the moon is there when nobody is looking. He spent 30 years trying to prove it. He was wrong. In this video, Brian Greene walks through the complete story of local realism and its experimental demolition, from the EPR paper of 1935 to to Bell's theorem of 1964, to the Nobel Prize-winning experiments of Aspect, Clauser, and Zeilinger, to the new evidence from quantum computers that has confirmed and extended the Bell results at unprecedented scale. Greene explains what local realism actually means, why Bell's theorem is a mathematical proof, not just an experimental result, why quantum computers cannot work if hidden variables exist, and what it actually means that the universe does not consist of things with definite properties when no one is looking. He walks through the three main interpretations of quantum mechanics: Copenhagen, many worlds, and Bohmian mechanics, explains what each says about the nature of reality, and explains why none is fully satisfying. And he follows the implications honestly to their conclusion. The strangeness of quantum mechanics is not a feature of some remote quantum scale with no connection to everyday life. It is a feature of the same particles that make up everything you experience. The classical world you inhabit is an emergent approximation. The underlying reality is something far stranger. Here is the physics that proves it. Subscribe to Brian Greene Universe for quantum physics taken all the way to its implications.